that goes on the screen as well as my voice, and yours is on record and not videotape. For the last 5 years, guys, I've been using this technology in my classroom. So my 5 year worth of lectures I've done with it are on YouTube, open to the public. To date, we have 1,400 hours, 1,400 hours. For a total of 625. So if you have an apprentice that need to know parallel series circuit, or he or she need to know wiring methods, or if you need somebody who need to know a little bit of AccuBid or McCormick or SKM part tools for window, or how to use this calculator, or grounding and bonding, it's all there. So nothing but electrical. So I like to do that, and I get a lot of feedback. I learned a lot by putting it there. So feel free to check it, guys. If you go Chad Kearney, type Chad Kearney, so you go there. This will be there too tonight, what I'm going to do over. Okay, so what I'm going to go over with you guys is commercial industrial load calculation. It's actually a project that we do with my students. My full time now is I teach electrical design. We do Revit. We take a building, and we do it in Revit and one in CAD. Actually, 3 buildings. 2 in Revit, 1 in CAD, and we build the whole power distribution system, the lighting system, as well as the low voltage system. So we do layout of lights, layout of power receptacles, circuitry, you name it. But what I thought to share with you guys is how to come up with the riser. Before I go ahead and start this, do we have a lot of engineers? Can you raise your hand if you're an engineer? So I be scared of you. Most of you, oh boy, now we're in trouble. The rest of you guys are master electrician, and I assume, and you design, and all of you. Okay, so what I'm going to share with you guys is engineers can do anything they want, but what I try to do when I do load calculations is kind of follow the code. When I say as long as you want, you can do anything you want, because we're PE, we're registered engineer. I can make a 4-aught carry 500 amp if I'm willing to lose my license, right? Are you guys willing to lose a license at my house? I'm not. So that's why we stick to the code as much as we could. So because we don't want to be sued. The code is a common denominator between a bunch of guys have got together, and they hopefully figure it out. So what I have for you guys, I do have a riser that I'm going to be showing you. This is the riser that I'm going to be doing. Again, this is a project that we do at our college. So I'll walk you guys through this riser. And then, of course, everything is based on 2014. You have to have the NEC code book with you, I have it. And then I'm going to show you the layout of the building that we're going to do. So we'll go over the building layout. So I have multiple things, and I have access to SKM. That's why I ask about engineers. If you have an access to SKM is great, guys. Resource in checking your size and all this stuff, especially when overcomputation device sizing for transformers and chillers and rooftop units and air handling units. So it's a great tool if you have it. You don't have to have it. And I don't know about you guys, but 5 years ago, I'm an engineer, so I have a lot of softwares. I got introduced to this calculator. And I don't work for the guys, so the record. And I can't imagine going into an electrical truck. If you're an electrician, I can't imagine being in the truck without one of these. Now, to use it professionally to the fullest, especially for electricians, guys, because engineers have a lot of other tools, and even as an electrician, I use it. The nice thing about this one is fast. The key word is fast. Okay, how many conductors number 12 THHN plus like 5 conductors or 6 conductors number 12 THHN plus 3 conductors number 10? I'm going to put them in a conduit. Just say that we typically don't do that. What size of conduit, EMT conduit do you need? In a couple of clicks, it's there. So you need to spend 4 hours though to use it professionally. I put a couple of my YouTube channel, bunch of calculation for it, and it's called electrical calc. So it's really great. It's easy, the fastest thing. It's fast. That's what I like about it. In sizing conduit, especially sizing conduit, because I don't like, you have 4 feeders, 500 kcm, 3 feeders, 500 kcm THHN, and another one for 350 for neutral and on the ground. Different sizes. What size PVC conduit do you need, or rigid, or EMT? Couple of clicks, you're there. Anybody have used this? Do you guys use it? Do you think it's handy? A little bit. Voltage drop problem. Gosh, unreal. So here's what I have. So I brought this one with me, guys. Let me share with you what I'm going to walk you with. Let me go and start with the Excel sheet. Like all engineers, we have a lot of calculation, guys, and sheets and what's not. So what I thought, and again, everything that you see today, if you guys want it, I'll send it to you free of charge. Send me an email, and I'll be more than happy to share it with you. So what I have an Excel sheet that we developed that takes step by step how to do load calculation, not only for the service, but also for every chunk of load that you have in your building, you decide to have in your building. So I'm going to walk you through this this sheet, but before we go there, we probably need to look at the building that we're going to be looking. I'm going to be taking you guys through. The building that we're going to look at is a 25,000 square foot building, half commercial, half industrial. So it's a big building. So relatively big, not too big. So let me see if I can have a picture of it here. And again, this is from a presentation we do. Okay, there you go. It looks something like this. This is all Revit, by the way. This is designed by Revit, by my students, under my supervision. So if there's any mistakes, I carry the responsibility. So that's your that's the industrial building. It's manufacturing floor. I would say 25% of it is maybe 30% manufacturing floor. The rest is supporting stuff for it. The building goes as here's your building parking lot. So we do all the design for the parking lot and what's not. The building is made out of 2 stories. That's what we're going to be sizing for, so you know where we are. We have the first story, have an open manufacturing floor right here with bus duct coming from the top and feeding all these machines, owner equipment machines. So what you're looking at right in this area here, this is all machines coming in here. So you need and we're burning them at 2 different voltages. 28120 and 48277. So you to complicate things. So we're running 2 bus ducts. Remember, it's for training purposes. You wouldn't do that typically. Right in here, and then we do have shipping area here. We have a hazardous location area, so that will introduce the people to the design hazardous location. You're looking at the lighting system, by the way, here. Mechanical, electrical rooms right in these areas. We're looking at some closets here for the low voltage. We have some stairway going up. And we have a data, to add salt to injury, we do have a data center here. So that's what I want to be sizing for. So we go into the PDUs, UPSs, size PDU, UPSs, and so forth. That's the introduction. And they're all selected for a reason. They're bathrooms, support areas, hallways, and this area is an open office and reception, and the main entrance is right here. So that's kind of the building that you're looking at sizing the service for it. Again, we're sizing a service, as well as all the distribution system for it. And I look forward to see your feedback on that one, guys. That's the first 2-story building, of course, remember. The second story, this is still the manufacturing area, all here. This is mezzanine here at the top of it. This is where the air handling units are located. And we have, this is a lab. In the second floor, they have a lab where they do a lot of experiments. It's an industrial plant, with supporting area, lunchroom, and an office and an elevator. So, and you are to come up with a complete power distribution system for this building. Again, it might be a little bit more than the engineering side or what's not. So here's your power switchgear, and things might be not to scale, guys. We're going to be sizing the switchgear coming in here, and bringing the power all the way to that red bus duct here. We're going to be sizing. So here's your switchgear right in coming in here into the building, and feeding with bus duct 480 all these machines. And then we have the green stuff is another bus duct 280. There are 2 voltages. Okay, so we're going to be sizing the bus duct, the 480-277, as well as the green, which is the 28120 bus duct. In here, there's a couple of transformers and a couple of panels to feed the building. I'll show you the riser, so just give you an idea. So a couple of generators in the back. So the building, we're backing up the building by generators, 100%. We have money to spend, like I wish we have it when we were doing a project. So you end up with bringing generators outside. The voltage to this building is 48277. We have a couple of transformers and termination box in the back. And we're bringing the power basically in here. And in the second floor, we're feeding all these mechanical electrical equipment. You're looking at a bunch of mechanical electrical equipment. So just to give you an idea what the building is, switchgear, receptacle panel, lighting panel, machine panel, bus duct that we're going to be sizing over here. Right in this area, there's a PDUs, power distribution unit, and a UPS system here to feed the data center. So that's where power-wise, focusing on the power, that's what we're going to be doing in this room. So a lot of you guys are an engineer. These decisions will be made when you deal with the architects, where the electrical room is going to be located, the size of the electrical room, and we get into the fight of sizing our electrical mechanical rooms, and having the real estate first. And then you get into so that's kind of the overall picture that we're going to be what you're going to be looking at. Any question guys about the picture? So a 25,000 square foot, two-story building, manufacturing floor, support area, data center, with an office area. And we're supposed to size the power. We're focusing on the power here. We need to size the lighting panels, as well as the receptacle panel or panels, mechanical equipment panels, as well as, of course, the main feeder and the bus ducts, using the NEC code book and the load that we have been given by our mechanical counterparts and process engineers. Does that make sense? And again, I apologize if it's higher than what some of you guys electricians are used to, but you can apply this rule to anything. You know, it doesn't have to be, the size of the building is a 4,000 amp switch gear, but it could be the same rules, guys, could be applied to a 400 amp panel. Really nothing, no difference in terms of the process. So let me put this one here and get you. So the first thing we need to focus a little bit on is the riser, come up with the riser. And I'm going to focus this one here, just to get you, oops. I want, okay, so this is good enough. You can see the big picture. There you go. Okay, maybe a little bit more, Chad. There you go. Trying to zoom into it to give you the big picture. Okay, so that's basically the whole riser. In the power industry, I'm sure a lot of us are engineers here, guys. We have something called the power riser. You have to come up with the power riser. That's the big, I call it the big picture. It's a skeleton for the building. And you sit there and negotiate. And the most important thing, being we have a bunch of engineers, we decide is what type of voltage system do we want to burn this building at. And being an engineer, the first thing you should say is 480-277. Efficient power system. But the problem with the 480-277 is you have to step it down to 28120 and feed receptacles. So there's losses in the receptacles, right, in the transformer. So I heard this over the years. You can agree with this on or not. This building is definitely a 480-277. But there are other buildings, guys. You walk in, 28120 will be the most efficient. A cutoff is 15,000 square foot or less. Your office building, 15,000 square foot or less. Ideally, this is a good application for 28120. More than 15,000 square foot, ideally, it's a good application for 480-277. So that's the major decision that you have to decide. Am I going to cut off? What type of voltage do I want to ask the utility to provide me? Electrical utilities, guys, will provide you with any voltage you want. So that's, I look forward to hear what you guys think. So this is definitely a 480-277 system. So here's how we start. When we design our risers and do our calculation, we have to make major decisions. Typically, when you think of any building, walk into any building, you need chunk of load for lights. Every single building you walk into, you need some type of a chunk of load for lights. We call this if a building is big, we call it lighting panel. Okay. Then we have another chunk of load dedicated to receptacles. Unfortunately, in the U.S., we burn our receptacles at 120. Most of the world, guys, they burn them at 240, so we don't have to have a receptacle panel. So since we burn our receptacles as 120, 208, 208, 120, we need a dedicated panel to get you to 120. So that will be your receptacle panel, typically, in any building. So we have receptacle panel, we have lighting panel. Again, this could be one panel if the system is small. Then you get into another chunk of load, which is mechanical panel. Every building you walk into, you have to have light, you have to have receptacles in there. Then you have to have some type of heating, cooling, ventilation system. So if your building is big, you try to think, okay, well, I'm going to go allocate another chunk of load for my mechanical equipment. Mechanical, heating, cooling, ventilation, rooftop, and these could be one panel or multiple panels based on the size of the system. So I have mechanical panel. Then if you're building, this is a little bit complicated building. So now we lit the building, we have receptacles, and we have heating, cooling in the building. The next step we'll ask yourself is, do we have a data center in that building? Or does the building have a form of data that we need to back up or have a special? This particular building, just for training purposes, we allocated a little data center in it. So we need to allocate a big chunk of load that goes to UPSs and PDUs. Again, these are not every building has that one. So if you have a room like this full of computers in part of that building, you need to allocate a load associated with a feeder that goes and feed this UPS, which in turn feeds PDUs to feed the racks, the computer racks, if any. So that's what you're saying here. We're bringing my power from here into that switchgear, and so that's my main panel. We have a UPS that feeds PDUs, two PDUs here. We have a receptacle panel. We have some lighting panel and mechanical panels over here. The other thing, so we have mechanical, receptacle, we have lighting, we have UPS panel. Now you're going to ask yourself if it's a manufacturing. Remember, this is industrial commercial. If it's a commercial, you are done. Right? What if it's part of it is industrial? Then you have to allocate a big chunk of load to your industrial process. That's what would be your owner equipment. We call them owner equipment. You need to burn the owner equipment. Factory, you need to allocate a big chunk of load or loads into that factory that we do. And that's what we did with this, allocate a big chunk of loads. So to summarize, guys, we'll have a service panel, service equipment here, and from the service equipment, you can start taking chunks of loads inside your building for receptacle lighting panel, receptacle panel, mechanical panel or panels, UPS, as well as owner equipment. So that's what we typically, we handle as an engineers and electricians, you handle a panel. Now, if you have a small shop, and you can put all your receptacles and all your mechanical equipment and all your lights all in one big 600 amp panel and distribute it right there, right? Does that make sense? So it's small, 600, done. A lot of you guys do that all the time. No sub panels whatsoever. So that's okay. The bigger the system, the more you specialize these panels. And to add salt to injury, we need to back up the system. So we have two generators here sitting, going underground and going to the switchgear. This is an ANSI arc switchgear, the highest that you can get, so we can parallel with these switchgear. That's the whole idea here. That's as high as, for the most part, as you can get with these equipment. So two generators back up the whole building at 4,000 amp level and distribute the power. We have a mechanical panel too for the air handling unit. We have two-story building. So we decided to put a mechanical panel too because of big chunk of load in the second floor, we need to feed them. You guys are engineers, the first question that we ask yourself, where should I put my panels, right? Without getting to details. You're going to put your panels as close to your loads as you can, right? But we don't have a whole lot of control over it. Sometimes we get close. That's a discussion that you do when we design the building, where we're going to locate our electrical panels in the building so we can minimize the voltage drop. Voltage drop is a big issue when you design any commercial industrial building. Bigger branch circuits, bigger feeders, voltage drop. So we're going to put them typically in the center of the building. Typically, if you have a building, every story building, it's nice to have a panel or panels for every story, so it feeds that receptacle and that lights if your building is big. Okay, so any comments, guys, about what you're looking at here, what you're trying to size? Again, that could be as high as you can get it. So, does it make sense? No? Yes? So I hope, especially the electrician, I hope I didn't, guys, get you uninstalled. Here's one sheet. When you size the system, let me show you before we go into this sheet. Let me show you what the owner equipment list. Here's what we typically, guys, get from the mechanical guys, if you can get them to get you something. So there are two, now remember, lights and receptacles, we can size them for the most part based on the code and based on what we put in our building. So we know our lights and receptacle in a building. Now, mechanical equipment, we have no control over sizing the rooftop unit or chillers or cooling tower right? Or air handling unit or units. So the first thing you need to go to your counterparts, the mechanical engineers or the mechanical contractor, if any, and again, is go get yourself a list of mechanical equipment. And this one, this is given, of course, as a list of mechanical equipment. You can see all the air handling unit, supply and return for 3 air handling units given here. With the voltage, the most important thing you need, the voltage and the power. Typically, almost all, it's if you have respected building, so-called, 3-phase. I mean, you'll be fool in our industry to power things with single phase if you can power with 3-phase. I mean, you always, if the mechanical come to you and there's a pump that you can power with single phase or 3-phase, what would you do? 3-phase. That's why we have 3-phase, superior. So 3-phase equipment, the horsepower is very important. And also need division control, who's doing it, division 26, us, or 23, the mechanical guys, and what type of starters are we supposed to provide, us or somebody else have to provide the starters. You can see we have a bunch of VFDs on that, so that will help us knowing VFDs and magnetic contactors right here. You guys are familiar with that one. So we have, and then we have conduit, and that's a schedule that we need to fill later on. But you need to get this list from the mechanical engineers. What we have done, I worked for wastewater treatment plants, short Hendrickson, and I remember going to the wastewater engineers and getting this information from them when you're sizing a service. They don't have it. So we developed, my boss and I, we developed a sheet that can size the building based on how many oxidation ditches you have and the size of the oxidation ditches and how many clarifiers and the size of the clarifiers. So we as an engineer, guys, if you do a hospital, the same thing. A lot of us come up with an idea above and beyond what the NDC code book. You can tell me how many oxidation ditches, I can tell you how many aerators and whatever pumps that from historic collective data you need. But that comes from collective, historic collected historically data. If you don't have this one, then you need all these equipment. So this is my mechanical equipment. You can see for the most part in heating, cooling, ventilation. So I have my air handling units. I have a big fat chiller here. Can you guys see that one? This is sitting, that baby is sitting at 525 kVA. That's a big chiller, big chunk of your load. So when you have a load that big, 525 kVA load, that's remember on average, a house can consume 10 kW on average, or less even. So 525 kVA is a big chunk of load for one piece of equipment. So you can tell how big these equipments are, plus the horsepowers. So that's definitely something to pay attention to. The reason why I'm saying this, because if you have a chunk of load like this, you might have to feed it directly from your service panel. So in this case, what we decided to do is feed it from the 4000 amp 48277 switchgear directly. Why? Because it's a big chunk of load. It would be waste to feed it from a mechanical panel and oversize your mechanical panel because of that single load. So these things, flags that you have to pay attention to. We have also the crack units. This is for the computer room that we need to feed over here from mechanical equipment. Some exhaust fans, and we do have 2 sets of environmental chambers that need to be fed. And because of their importance and because of their relatively large size, not too big, but their importance, we decided to feed, you can make this decision. We decided to feed them directly from the switchgear. So then you start asking yourself, is this load too big so it has to be fed directly from the switchgear? Or is this load too important that I don't want to lump sum it with other loads and I should feed it from the main panel or the main switchgear? So that's your mechanical equipment. Any comments, guys, about mechanical equipment? Based on this information that you see, you will be sizing your mechanical panel or panels, as well as your service. So that's your load. You go down here. The building that I showed you guys is a commercial industrial application type building. And there's a manufacturing floor, and the owner of the company and manufacturing engineers give you a list of so-called owner equipment list. They're cooking things in their factory. So what are you cooking? What type of equipment? So you need to ask for this. So here's all the equipment that we have, tube mills, and they're all labeled, you can see, with numbers because they are laid out by the process engineers in the plant. So because I want to feed them with a bus duct, so you need to know how they are laid out so you can size the bus duct to feed them. And just to bring to your attention, for example, machine 1 Tube mill, I have 12 of them. The voltage, they need a neutral, so they're running them at 208, 120. Don't ask me why. And each one of them is 13 amps. You could be given this equipment as kVA or amps or full load amps or whatever the form that you get. We got them to amps. If we get your amps and your voltage, then you can get your kVA anyway for all these equipments. So anyway, so this is machine one. I have another machine that, for example, I have machine number 6, buffing machines. Don't ask me what they do for a living here. This project's supposed to be, guys, modeled after Boston Scientific for training purposes that we do. So this is medical stuff. So I actually want to go to the one underneath it, the cutter here. Machine number 7 cutter. I have 3 of them, and they're burning at 480. So it's so important. There's a few machines that are running at 208 single phase, 2. And don't ask me why they decided to run them at 208 single phase. Maybe because they don't have them in 3-phase 208. Okay, so that's you can see that there are 2 types of loads based on 2 voltages. So when I design my bus system, I have to take this into consideration. You can't plug it. You have to design 2 buses or whatever your solution for this problem would be. Okay, so that's the second thing that you need to get, because you can't get from any sequence book. This information, there's nothing. You have to get it from the owner of the building and the mechanical engineers. So after you do that, you get all this information. Then you build your industrial load calculation sheet. The cheapest software that you can buy, guys, is Excel. I mean, if you're a master electrician or an engineer or anyone who does sizing and you don't use Excel, you're really behind. Excel can get you a lot of things done, calculated faster. So what I'm going to start here with, again, load calculation. The first thing we'll start, like we said when we were talking about walking into any building, you need a big chunk of load allocated to your receptacle panel. Like I said, everything that you guys can see, I can email it to you. I don't have handouts. Drop me an email, email you all these sheets. Okay, so the first thing I need to do is allocate receptacle load. Now remember, this is not dwelling where you can go and find your multiplier for. This is a commercial industrial. There's a decision that you have to make. If it's a non-dwelling building, the code allocate 180 volt amp for every receptacle that you as a Mr. Engineer or your designers have decided to install in this building. So that's a lot of the time we use this one. There's also, if it's a commercial building, the code allows you to have 1 volt amp per square foot for the commercial building, office building, commercial office building. This is multi-use. A little bit of an office building, the rest of it is a commercial. So what we did is we designed it based on laid out our receptacles, all the receptacle in this multi-use, and allocated each one of the receptacle 180 volt based on any sequence book. Now you can have, the question I get asked, well, we haven't designed the building yet, right? You guys, what do you do when you don't design the building? Either use your experience, say, oh, it's going to be 225 amp panel anyway, stick it there, or you can, I used in the past 1 volt amp per square foot is a good approximation because we use it for office building based on the code. So it's a good way of getting a handle on what is the allocated volt for your receptacles, 1 volt amp if you don't have these numbers. That's a good, and the code says for an office building, guys, this number derated or 1 volt amp, whichever is larger. The code says for office building though, but for multi-use like this, technically you're supposed to go take the office part and apply the office to it, and then the thing, and that becomes really splitting hair sometimes, but that technically how you can do it. Okay, so what we did, we get the numbers. We have 99 receptacles in this. We also have quads in the whole area. We have quad, and the quads are allocated 360, which is double the duplex, right? Double duplex. A quad is double duplex. The code says you allocate for a quad double the duplex, basically 360. So we have 80 quads in this building designed, and 99 duplex receptacle. Cool. That's coming directly from 220.11i, allocated 180 volt amp per square foot into your receptacles. Then you do the math, and I did Excel sheet, guys, because you can see the math is not really rocket science. You can see at the top here, you take two cells and you multiply them by each other, right? Can you guys see that? If you're familiar with math, here's equal cell E4 times G4, and that'll get you multiplied by each other, right? Then right underneath the same thing, you multiply the number of quads by the allocated volt time for these quads. Piece of cake, right? Using Excel. Then you add them up. We have also sections here. We have what do we call them? We have fixed multi-outlet assemblies. Fixed multi-outlet assemblies. In this project, we're using, again, the judgment you have to use. We're using multi-outlet assemblies in this particular project. And the code says if they are simultaneously used, you can allocate a 180 volt amp for each 1 foot of them. If they're non-simultaneously used, you allocate 180 volt amp for each 5 feet of them. So that's a judgment that you have to use. If you are in doubt, what do? Always lean on the side of safety and assume they are simultaneously used. We have 480 feet, guys, and these benches, remember I showed you in the second floor, they have all these benches, multi-outlet assemblies in that area, feeding all these benches. So we're decided they're simultaneous, it's their factory, so they're using them. Testing. So we allocated 480, there's 480 of them. Each one of them is going to have 180 volt amp each foot. And when you do your math, you're going to multiply them. It's really easy. You take the 480 volt, not volt, 480 feet, multiply by 180, and that's what you get. Any comments, guys? So we allocated the quads, the duplex, and the multi-outlet assembly based on simultaneous or non-simultaneous. You guys do that all the time. Any comments about that one? So then the rest with Excel sheet, that's why I didn't put them in a PowerPoint presentation, because Excel showed you how the math is behind it, not like it's rocket science. So you total them. So you're totaling basically the multi-outlet assembly with the receptacles, quads and duplex. Cool? So, so we total them right in here, the sum of the two. So that will be the connected so-called, if you use SKM, that will be your connected volt amp in SKM, the connected, just the connected. Now it's that's a judgment thing that you need to do too. Now remember, being a professional engineer, guys, you can do a lot of judgment. You try to kind of stick to the code, so if somebody sued you, you can justify your, what you have done always, right? We're trying to justify what we have done. Okay, then the NEC code book says in receptacle demand factor for non-dwelling 220.44, you guys are familiar with that one. It says anything higher than 10, they're sacred cows, the 10 kVA, leave them alone. Anything higher than 10, chop them by half. You guys are familiar with this one, you've seen it many times. So what you do is you take this chunk of load, the first 10, leave them alone. In the math, this will be the over 10, cut them by half, and that will give you the 10 plus the half of the over the 10. Can you guys see this scale here? Does that make sense? I'm not an accountant, but, and right in here, then you add them up. So your allocated demand receptacle load, I call it receptacle load, right now is almost 72 kVA. 72 kVA. Can you guys see that? 72. So that's going to be where you size your receptacle panel. They're going to size from your transformer for that panel, and you're going to size your feeder, and you're going to size a bunch of other things. Any comments, guys, about the first chunk of load that you encounter in any commercial industrial building? The receptacles. Like I said, I've been in the buildings, guys, where you don't have a receptacle. I use 1 volt amp per square foot, and that will give me a good understanding of what you did. Any comments? I look forward to hear any comments. I know we're engineers, we do a slightly different maybe, but I try to stick as close to the code as you can. So then, what I did in this sheet, and you don't have to do that, but that's one way of doing it, is we have columns here. So you see that column, the first column is sizing the switchgear. So I need to pull all this information in one sheet and size my switchgear. So I pulled, you can see here, I pulled this number in here, so it can be counted now under that column to size my switchgear for me. I want to take you so I can walk you down here too. The second column is located to your low voltage panel, or I call it receptacle panel, but call it P1 or LP1, whatever you want to call it, but just to make it identify it by function, call it receptacle panel. And you agree with me that this chunk of receptacle will be seen by the main switchgear, and at the same time will be seen by receptacle panel. I can't get to the young fellows at my college to understand that Chad is coming from the receptacle panel. Why are you putting in the switchgear? Well, it has to go through the switchgear to reach the receptacle panel, right? Or whatever panel. So power goes, you can't transmit power wireless yet. We're working on this. So you zoom the power into the receptacle panel without going through feeders. Okay, so just to show you what the column is here, so you know as we go through. Here's my receptacle panel. Right next to it, I have a column, guys, for my lighting panel. Same thing. I have my mechanic. I decided to have, we talked about the chunking them. Again, feel free to disagree. You could probably group things together, and that's one way of doing it based on the code. I have been told in the past, and when you chunk your load, guys, you don't want a load to, you know, especially the lighting and receptacle panel. You want to stay within the 225 amp panels for lighting panels and receptacle panels. That's kind of within, give or take. If you go higher, like 600 amp lighting panel, imagine how many branch circuits you're going to bring, especially if it's 48277. How many branch circuits you need to bring to a 600 amp lighting panel or receptacle panel? Voltage drop issues, so 225, maybe 300. That's good, a good number, at least in my mind, when I do receptacle and lighting panel. I want to stay within 225 amp panels, 300 amp panels, but definitely not 600 amp. Anybody have 600 amp receptacle panel? Maybe for, and we're not talking about PDUs here for data. That's a whole different story for racks and what's not. So this is my lighting panel. We'll go through sizing it. Here's my mechanical panel one. The mechanical equipment that I showed you, the load, guys, we divide it into two. Why two? Because there's a lot of loads in the second floor of this building. We decided to take, instead of pulling all these branch circuits all the way down to the first floor mechanically, we're going to take all these branch circuits from the second floor to the rooftop units as well as air handling unit. This is a decision that you can agree or disagree with. But that's how you have to do it. So I have mechanical panel 2. Now remember, this building is a manufacturing building, so you need to allocate a bus. We decided when you have a manufacturing building, guys, a major decision you have to do. Are you going to feed these machines individual branch circuits? That's one way of doing it. There'll be a lot of them. The other decision that we typically do is we have a bus duct, run that bus duct over the machines and plug in your machines with a fused disconnector circuit breakers with SO cord and call it a day, right? And you feed all these machines, each machines, and that's what we typically do. To add salt to injury, we decided to run 2 bus ducts because we have 2 voltages. I guess we could plug a transformer. It would be too expensive for each machine. A little transformer that take 480 to 208 and feed the machine. Would you do that? Or would you group them in one big chunk of a bus duct? I thought grouping them in another bus duct because of voltage. If I'm to design this building, a real building, I would go to the the manufacturer and say, can you find these machines with 480? That will solve the problem. But if they can't, that's what's your solution. Okay, so these are your 2 bus ducts. UPS, this building have a data center, so you need to UPS it. You guys are familiar with UPS, 15 minutes worth of batteries to back up that data center in that particular little data center in that room. It could, if you don't have any of these, you zero it, right? You don't have to account for it. Then out of the UPS, typically we have a PDU. 2 PDUs fit from the same UPS, so 1 PDU fit from the same UPS, power distribution system, and UPS is uninterruptible power supply with battery backup, and this is my PDUs. And the last thing, guys, in this building, we typically, if you have a bigger building, you have allocated an emergency panel coming from an auto transfer switch backed up by emergency generator, and that's what you're looking at the other end. We need to allocate our emergency load onto the emergency panel. You can see how these columns, each one of them, I want to be pulling info in each and every one of the columns and populate it. Did I put anybody to sleep yet? You guys decided you should have come to the medium voltage. It makes sense, this. So, and when you think about it, guys, it's really not a whole lot. So we allocated the first chunk of load. Now for our receptacle panel, we chunk them as 72,000 volt amp on both the receptacle panel, and it will also be seen by the switchgear. The second thing, any building, and I started them this way, guys, because that's typically what you do. You walk into a building, you need a receptacle, and you need lights first. And then you need to heat and cool the building. And then after that, you start asking yourself if I have any other system. Okay, so unknown receptacles, I add this one, unknown receptacles. We have a situation where you guys have an unknown receptacle sometimes. If it's an office, here's how I handle the unknown receptacle personally. I allocate the 1 volt amp per square foot based on the office building. Just because I have no idea. They want to expand in the future. They want us to allocate size for expansion in the future, and they want to size the service for expansion in the future. So that would be a good application where you allow 1 volt amp per square foot for that building, and big chunk, have chunk for the future. We don't have anything on that one. So so that's my receptacle. My receptacle load. I'm gonna skip the load here. I'm gonna go directly to. You know what? Let's just start with. No, this should have been here. General light. Let me go to the general light, guys. Step 4. I should have put it before. General light. So we walk into any building, guys, and you need, now we have a chunk of load for the receptacle. We need to allocate a chunk of load. We need to allocate a chunk of load for, should be 220, isn't it? 220. Okay, so we need to allocate a chunk of load, guys, for the lights. Here's a couple of things for a commercial industrial building. What you do. Now again, for an office building, the office commercial building, the code says 3 volt amp per square foot across. Or you go to split hair. Take the support area, take it, I can't remember, 0.5 volt amp and what's not. Compare this value to the actual lighting fixture that you designed. You don't know that. When we start, we have no idea what lighting fixture we do, right? So you can, when you have your design, if you reach that point, you put all your fixtures based on the volt amp that you have and the number of fixtures that you have, and their continuous loads, so you add them up, multiply by 1.25. So what I do typically is I use 3.5 volt amp per square foot. I treat it like an office building. I know it's a little bit, you can get a little bit less than that if you split hair, especially with the VFDs right now, or using, not VFDs, using ELEDs, thank you. ELEDs with lights, you can get much lower than that. So what I do is I take the 3.5 times the square foot of the building. Here's the actual square foot, 24,000 square foot, multiplied by 1.25 continuous load, and this is 104. 104 kVA is allocated load for my lighting for the whole building. Right next to it, guys, I compare this one to my actual lights in my building after I get them. After I get my fixture, including indoor lights and outdoor lights and receptacles and what lights, indoor, outdoor, and parking lot, I'm sitting at 61. This should be, okay, so this should be 61 based on that one. So, yeah, 1, 2, 3, yeah, 61. I'm sitting at 61 actual load compared to code of 104. So what would you do? In 2014, guys, the NEC code book, when some of the changes allow you, if you can prove that this is the load and monitor and you can't overload your circuits, you can use the actual load to size your circuits. I don't know if you take, or another way is to, that 3.5 is an assumption, assuming it's across the road, a commercial building. You can go there and treat the support areas and try to get lower values by treating it area per area. You can get lower. So, like I said, this is a big assumption, really. You can slice it down into lower and make it rocket science, or you can, what I did is I took the 104, the code says you take the 104 or your actual, and you use the largest of the two. except in 2014, if your system is, I can't remember the language that they use, is monitored and you cannot exceed what you designed for, then you can use the actual load of the volt amp to size your panels. Anybody's doing that, taking advantage of this yet? We're not in 2014 yet, July 1st. Is that what we're going to do? So anyway, compare the two together, and I pulled this information basically. I allocated 104,000 volt amp, gentlemen, for my lighting load for this building. Now again, you can sit there and slice it down differently, get a lower number, you know, but with including the continuous load right into it, including the continuous load. Any comments, guys, questions about that? So that's my allocated load. And then on the other side, you can see I pulled in two cells here. One cell is for the switch gear, and the other cell here is going to be, if you look at the top here, it's going to be allocated to my lighting panel. So at the same time as you build it, you pull this information under the switch gear, because coming from a switch gear, and build your lighting panel as well. Under this, you don't have to do it this way, but that's one way of doing it. So any comments, guys, about the lighting load? 220.12, 3.5 is commonly used assumption. Your volt amp for your fixtures, add them up, and if they are larger than what the code allow you to, then pick the largest of the two, actual or 3.5 volt amp. I can't emphasize, so you guys don't be mad at me. This number here can be reduced if you want to go and slice the area, slice it slightly different. Okay, so we calculated the lighting load, guys. Based on this, I'm going to go to, so we got these one. I'm going to go to lighting load. Okay, so let me go to another chunk of load that's called data load. There you go, right in here. So data loads NEC 645.25. That came in 2011. It allows you to use the actual volt amp for your servers, or an engineering method. So I don't know if you guys size data centers, but what you can do is what we have done. There's two methods: is the square foot method and the rack method. The square foot method, you allocate a volt amp based on the servers that you're using for the data center, and you multiply it by the square foot of the data center, call it a day. And I believe we're moving more towards a rack method. So every rack will have 5 kW or kVA, equivalent, kW, kVA. So 5 kVA for every rack. Tell me how many racks you have in this data center, slam them by 5. You get this information from your data engineers and the servers they design. Anybody design data centers, guys? Feel free to email me so I can correct it if I'm wrong. That's what I hear from the people that I deal with. So for this project, guys, we allocated our data center in this area is 1,800, close to 1,800 volt amps, 1,800 square foot, little guy in that room. Yours could be 2,000 to 10,000, 100,000 if you want it. And this is only the area that you put where your racks are. We are allocating 150 volt amp per square foot based on the servers that we're using. Yours could be different. Then you increase efficiency. Obviously, when you size your servers, guys, they're going to be chewing the electricity. You need to allocate. They're going to go through transformers, and they're going to go through a conversion AC, DC, AC again. And so there is a factor of efficiency. Safety factor would be 10%. So that's where that one efficiency, 1.1, I'm multiplying, I'm adding 10% efficiency because of efficiency to this load. And then continuous load, and you can sit here and argue with me about that one. Because that's definitely continuously running, like lights, I'm going to increase it for safety factors and what's not, 125%. Gentlemen, I came up with 375 kVA allocated for my data center. If you don't have this in your building, what do? Zero it, right? You don't have to have this. If you're using the racks, like we're using next year, you put how many racks you have here, say 24 racks, and multiply them by the volt amp per rack, and increase them 10% for the most part. And you can argue with the 10%. You can get this from the manufacturer and what's not. But that's kind of cover your butt type of design. You know, you don't know a whole lot about the system. So we allocating, gentlemen, 375 kVA for my data center. I pulled this under the switchgear, you can see, and I'm going to pull it all the way down to my PDU, under my PDU, and under my UPS on my PDU. These are the numbers I'm going to be sizing my UPS and my PDU from the get-go. Does that make sense? So my PDUs and UPSs for this particular step of the process. Any comments, guys, about the data load? Again, if your multiplier is different, your efficiency is different, feel free to manipulate it. I don't know, you guys probably agree with me. When you design a system, other than data centers, when you design a system, you're lucky. There's something we call it load factor. You're lucky if you can get 50% actual load on the system. 50, you're lucky. Unless it's data center running a lot, but 50%. So if your service is 4,000 amp, did you work in a building where your service 4,000 amp and you go look at the meter and it shows 4,000 amp? You guys work in a building that actual 4,000 amp in a building? Like I said, you're lucky if you can give 50 load factor, 50%, 50 to a third to a two-thirds. That's what the load factor that we play with on a whole building. So because of all these factors that we put in. Okay, so that's my data load. Any comments, guys, about my data load? Allocating the data load for it. So you have to keep me. Yes, sir.
The numbers you use to determine the load, those are in the code or those are?
No, these are data getting from the engineering firm through the computer engineers. So they go by server. The servers that they use in these data centers, right now, I believe it is 200 per square foot, but they're moving towards racks. So you have a rack going up, and the rack, I think, is 5 kW. So they allocate every rack you want to put in this, and a rack is, what is it, 2 feet by 2 feet, give or take, right? To maybe 3 feet by 3 feet rack, and going all the way up to, what is it?
20-inch racks.
Is it 1 inch? Okay, so that's something roughly, yeah, 1-inch racks and going all the way up to 8 foot, maybe 7 feet, something like this. And you fill them with servers based on the specification. Are you guys using 5 kW?
No, I don't do data centers, but typical.
Yeah.
Ink shredding for the 4 post guns.
In 20?
19-inch, 20-inch wide, so it's.
And you're right, I'm going out of memory. I could measure them, we have them. But these numbers I get from Mishat Cooley because they designed them. Mine, when I did it 10 years ago, it used to be 50 watt per square foot. Now they went way higher than that when they designed the data center. Yeah. 100 and 200, but they're moving towards racks now because it doesn't matter what the square foot of the area. Give me how many racks. So we have 50 racks in this room, multiplied by 5K, and that will give you a rough idea of what your sizing your system is. Okay, that makes sense? Okay, so that's your data. Then now keep in mind, let's go, where's my mechanical equipment? I want to jump, guys, to this, my mechanical equipment, because, and I'm jumping, you know what, let's just stay in step by step. Let's go to the owner equipment, as long as just go in steps. I should probably switch him around. Owner equipment. Now remember, owner equipment, the one I use, and you feel free to disagree with for owner equipment, code-wise, justify it. So if I go to court, I use 600 for owner equipment, 670.4a. I hope I did it right. Anybody want to check that one? These are machinery. The machinery. So when you go to the machinery, guys, these are continuous load. Machinery, they're working, cooking things in your factory. So this is really, there's not a whole lot into it. You're going to go get all your equipment, list them. Remember, I showed you that information. And they're continuously worked on. So we're going to multiply by 1.25. They're all running at the same time. There is a demand factor. I call it engineering factor here. If you look at, there's a lot of equipment in that manufacturing floor. So then you sit with your process engineer and said, what's the likelihood that all these equipment, count them, number of units, all of them are fully engaged at the same time? The non-coincidental load. So I use the factor of non-coincidental load. They're really highly unlikely that every single one of them is going to be engaged at the same time. So the way I do it is I multiply 0.8 is Chad Curry factor. So I basically offset the continuous load. I assume they're non-continuous. So I get rid of them. I multiply by 1.25 because they're continuous, and then I derate them because they are highly unlikely they're going to run at the same time. I put that 0.8 and offset the continuous load for them. So basically, I add them nameplate value. Done. No continuous. Why? Because really highly unlikely they're going to be all running at the same time. And remember, we're sizing feeders and branch circuited. When you feeders and services, if we size a branch circuit, that's a different story. You know, they're right at the feeder. I mean, it's highly unlikely they're going to be running. Again, this is really a factor I feel comfortable using. Just basically add them up name value. Okay, so we added them up, gentlemen. We have 914 kVA load allocated to my owner equipment. If you can see, there are some of them are red and some of them are black. Can you see that? That's because some of them are running at 208 and some of them are running at 480. So some of them running at different voltages that the kVA is coming from them. And again, you can put the amps here if you want to. So I can't remember which one of them is the 208, but we'll see in a second here. So this is the allocated load for the manufacturing process. Nameplate value, add the nameplate value. Then you go here, you pull this number, guys, right directly under the switchgear. Remember, J is a switchgear, sizing the service. And as long as you're on it, you pull them under two different numbers here. One, now, this is where you're going to use kind of your imagination in Excel. So we're picking all these and we're assigning them under, which one is that one? I think the 480. Now, yeah, there are two buses. The 480 are going to be under the 480 bus because we're sizing a 480 bus, and the 208 are going to be under the 208 bus. Right? So because we're going to feed them from two different buses, right? So here's what we got. So that's why they are pulled and they're split basically, right at this level. They're split into, it looks like 150, 51 kVA was 208, and the rest of them were 480. Cool. Now, as I move through, I'm sizing my my bus duct coming out of the switch gear to these pieces of equipment. Any comments, guys, about the owner equipment? Remember that calculation, we call it industrial commercial. So that's where the industrial part of it. And we have this, you can walk into any factory and get this information. So, okay, so we got these. This is all my load. So we got okay, so we got this owner equipment. Let me go lighting. We got these. I'm going to go down to okay, non-coincidental load. So I picked my general lighting. We talked about general lighting, guys. We talked about, there's track light. I have a couple of track lights too. For the building, I have track, that's where you can go to the NDC code book, guys. And yeah, I should probably talk about step number 8 too, before we move into the lighting. If lighting load demand factors, for most of the stuff that we do, guys, not a whole lot. Hospitals, sometimes they apply demand factor on lighting, you cut them down, but it's good to go check 220.42 if you see any demand factor that you have to apply for lights. In our case, we're not doing. Second thing is a track light. If you have a track light for that particular building, that typically for a track light, 150 volt for every 2 feet, continuous load. I have 10 of them in this building, in addition to the general purpose lighting, and I multiply them by 150, guys, and that will get another allocated load on lighting load. And you can see how I pull it down. See how I pulled it down here because they're under the lighting load. They're special lights. So you start pulling these special, that's why I make it columns, because if there's anything that also have to be in the lighting load but goes downstream, you start pulling it and put it in the column as you size it. There's also this step 10, sign. The NEC code book, guys, 220.14F and 600.5A require every commercial building accessible to the public from the ground to have a circuit and a load allocated to a sign. It doesn't, if you don't know that, it doesn't matter because it's really peanuts in the bottom thing. So that's why if you forget them as an engineer, I mean, really, when you talk 1200 volt amp compared to we're down to the mechanical equipment is almost a mil. So it's 900,000. So that will allocate it. Here's a 1200 volt amp per 1200 amp per sign. We have one sign, continuous load because it will, and up it, and we put it under the switch gear, and this will be burning at 277. So I went and I put it also under my lighting lamp because I'm going to take it out of my lighting panel. You could have taken it at 120 and took it out of the receptacle panel because you just slice it to wherever you want to feed it from, if your sign is 120. So this is a 277 sign, and we're going to pull it from there. So that's a couple of other loads that you can do, sign. If we have show window, and I'm going through the step-by-step, guys, 220.14G, ask you if you have a show window. It goes by 200 volt amp for each linear foot. So take that linear feet in your show window, multiply them by 100 for your show window, and then that's where you get your, I don't know if we have any of these, 200 volt amp. We don't have any of them. So you just put them 0. If you don't have them, you put 0 in it. Right underneath it, we have kitchen equipment 220.56. That's for commercial kitchen equipment. If you have any in that building, you can also allocate for it. I don't know, I have a dishwasher, I put it there, it's peanuts, somebody can agree with it, agree. I'm allocating a dedicated circuit for a dishwasher, and I'm throwing a 24 volt amp for it, and I'm putting it under putting them under the switch gear, and I don't know why we put them under the lighting panel or the receptacle panel. Yeah, they went on the receptacle panel. And again, these are peanuts in the bottom things, but it's nice to keep an eye on these, add them. So these are not the big chunk that makes or break you. Then we go into step number 13 and 14, guys, especially 14. 14 is your loads, your mechanical loads. These are the heating cooling for your building. How are you going to heat and cool your building? And also non-coincidental loads. The loads that will heat and cool will not run simultaneously for the most part, right? Fully. So you need to allocate, turn them off. You're familiar with that. So let's start with the non-coincidental loads. I have a chiller. My chiller is going to be the largest load that I'm going to have. My chiller and my heat, guys, I'm heating with gas. A lot of us heating gas in Minnesota, right? So my gas, I don't have I'm not burning electricity to heat. So the only thing here I have really allocated to the heat, and you probably dig and find a couple of pumps that circulate too. But the only one I have is a 20 amp circuit control circuit. I allocated a 20 amp 120, and I allocated 2400 volt amp. You're going to see compared to the chiller right here, the chiller is 525 volt amp, just the chiller, 525 kVA. So it's way over. So it's going to overtake it. Right underneath it, I have a cooling tower. Allocated this amp from the NEC code book multiplied by the voltage and multiplier for the 3-phase. And I do have my 540. The cooling tower is also allocated here. But you typically compare this one with this, the two, the cooling tower with it. So you can see it's way higher, the equipment, the cooling versus the heating. So you pick the largest of the cooling or heating. And in this case, I have 579 kVA allocated to cooling the building. And then I pulled that number under the switch gear from 1, and I'm going to go pull it also under in 2 application later on. I'm putting it under the switch gear. You'll see how we pull it under. The chiller and the chiller, guys, are fed directly from the switch gear, so we don't pull it anywhere else. Then we go into the other equipment for circulating and what's not. I have a bunch of exhaust fans and chilled water pumps and what's not, and air handling unit. Air handling unit will work with both heat and cool, right? And I have exhaust fans and I have water circulating pumps for domestic and chilled. All these related to circulating the chilled water in the building or domestic water, if any. Well, there will be some. And crack units, can you guys see my crack units are here too? The cooling units for the computer room, all these loads, horsepower loads. You add them up, that's my mechanical load in addition to the chiller. And add them all up and increase, the code says increase 25% on largest motor, which bottom line, when you look at a load that size, 25% on largest motor is nothing. So and then you add them all up, all these motor loads, they call them motor loads, and then this will get you close to 480 volt amp allocated for your motor loads. All the exhaust fans, the pumps, these ones, guys, the reason why they are here, these are the cooling units, special cooling units directly related to the computer. They run winter and summer. Doesn't matter here because we're running the cooling as the highest. So that chunk of load, gentlemen, is the load that we're allocated for heating and cooling. You pull it right in here under the switchgear, and then when you go up to this side, you split it. Can you guys see I split it? I have two panels. I split them. I don't know if you guys can see way at the top. I have mechanical panel 1, mechanical panel 2. So I decided anything floor in the second floor or higher in the roof, there's a cooling tower, I'm going to pull it from mechanical panel 2, right? Anything in the first floor is going to be pulled from mechanical panel 1. And that's why you see these are pulled into two different locations. These are pulled into two different locations. So, any comments, guys? Any questions about that? Comments? So that's your mechanical load pulled. I don't know why I put this number here, but we'll zero it. Probably I typed 2 when I was going through it. So, so that's your mechanical load pulled with the chillers allocated. And then that's it, basically. And then at the end, I want to see if I can get all of them in one sheet. Here you go. So that red line at the end, we have a load of, it looks like 2.5 meg for this building. And I have a load of this amount for my, that's my receptacle panel. So my receptacle panel have this amount of load, which is 74. My lighting panel, 107. My mechanical panel, is that mechanical panel 1 and 2? I believe. These are the loads on them. And then the bus ducts, and then the UPS and the PDUs. And you can see how this correlates with the numbers at the top. So now that's you captured, what you're looking, guys, gentlemen, is you captured every single load. You can adjust it, tweak it, make it different, but for the most part, that's what you do when you allocate, when you have a sheet like this that calculate all the stuff for you. Any comments, guys? Any questions? Comments, questions about that? Does it make sense? So similar to what things that you guys do? Again, you can agree with the numbers or adjust them slightly differently, but I think if you take a sheet like this one, especially engineers, you do it, or electricians, if you do something like this, guys, and something goes wrong, your chances of winning a case is higher. I hope. Because we, as registered engineer, we can, size things in any way, shape, or form based on experience, based on a lot of stuff. It's nice to substantiate your size, though. After I came up with the 4,000 amp switchgear, guys, I could sit there. Utilities do that all the time. And say, you know what, every single building this type we sized, we put a 3,000 amp switchgear for your switchboard. What makes this different? So I can go sign off on it and make it 3,000 as a professional engineer. You as a master, you can do that, but you're taking liability if something happened or whatever. So I like what utilities do. I used to do medium voltage. When I was working for SCH, we used to, at that time I was working for doing utilities, we used to take this calculation and we call it, and utilities still call it, architectural calculation. All that stuff that we've just done, and they call it architectural calculation, not even engineering. And then cut it by half. So 4,000 amp switch gear, 2,000 amp switch, 2,000 amp transformer sitting there outside for you. Do you guys see that? And in order now, the problem that we created is now their number of conductors pulled and our numbers are like this, 2 conductors to 5. So how are you going to match 2 conductors from one side to 5 conductors? Because of all this, now we have the termination boxes. Over the years, we came up, well, we don't care what you do on your side. From the service point, we want you to provide a service termination box size based on your architectural calculation, and from our side we bring half of what you brought basically. So I'm sure you guys deal with this one all the time. So half to a third to 2/3 basically what you do. Okay, so now after you capture it, we don't size, most of the equipment that we size, guys, is based on the amps. Then I go divide my voltage system is 48277. So you can see the math there. So I'm taking that cell at the top and dividing it by 48277. Here you can see that, that cell right here. And then the building that we have been told, again, that's where you're going to use your judgment, we're going to have a future expansion on it. You don't have to. So that number right at the bottom is actually 25% future expansion. Increase, that's engineering. The owner wants to increase 25% future expansion on that building. You don't have to do it on the whole system. So again, you could make it 0, but that was a requirement, future expansion 25%. Then you basically take this number and up it 25%. You don't have to do that if you're not upping it, but it's a good idea, guys, to kind of think of what. Sometimes if you want to expand 25%, you don't have even room to expand. But if there's no, you put 0 here, and you can see we're expanding. We're going to expand. We're assuming that they're going to add circuits to all these panels in the future. All of them have capacity for future expansion. All the panels, including the switchgear, 25% capacity for future use. You don't have to do that again. So you can see how all these numbers at the top, we multiply them by 25. So gentlemen, you end up with a switchgear of 3,805 amps. And your next, okay, now what do you do after you get your amps? At the level of up to 600 amp panels, no problem. The code says you go to the next standard overcap protection device. Now, that's cool when you're dealing with say, 600 amp or less. You start doing higher than 600 amp or 1,000, definitely 1,000 amp or less or more, you start dealing with adjustable circuit breakers. So I can really, there is unlimited amount of circuit breakers that I can deal when I have a fully adjustable circuit breakers. Because you can adjust them in any way, shape, or form. There's a plug that you can do. There's settings that you can do on them. So when you keep in mind, if your system is 1,000 amp or typically 1,000 amp, you're most likely 99% of the time, if you're engineering, you will be dealing with almost fully electronic adjustable circuit breakers. They can be molded cases, fully adjustable, or they can be like our switchgear, drought arc type circuit breakers. It doesn't have to be. It could be also molded case. Circuit breakers adjustable. 1,000 amp or higher is a good application for it. Best application. A good application 600 amp or higher. So I don't know what you cut off, guys, but that's one thing that you do. So then this is easy because my next size up is 3,800. Is really, we're very close. A 4,000 amp switchgear. Now right here, I can take this number, cut it by half, guys, and size 2,000 amp. I wouldn't do 2,000, but 3,000 amp switchgear with all the. I'm sorry. You, yes. So they run them hot. Generate revenue. Yeah. So you follow the step-by-step by code. You go to next standard up, and my switch gear or switchboard is for 4,000 amp. That's the size of my switchboard. Where do you go to get that number? For the most part, guys, for most of the project, we're going to go to step 19. You can see you can go 310, you can go to 240.6. Minimum panel size or size of the NEC code book, guys. When you size a panel, the size of the panel is the size of the overcome protection device that protect the panel. Though in real life, the size of the panel are different than the size of the circuit breaker. You could have a 300 amp panel with a main ahead of it, in it, or above it with 200 amp, right? Or 150. So, but the code, when you say a panel size, the size of the overcome protection device that protect that panel, inside it or outside it. So you go to 240.6, and that's what give you the size of that panel. So I came up, gentlemen, with a switchgear of 4,000 amp, a receptacle panel of 300 amp. So that's good. Maybe you can think, I had students in the past came and say, can we split them into two panels? Chad, put one in the second floor and one in the first floor. That's a good idea. You're looking at 150 amp panel, upper or lower. Maybe that's a decision that you make. I like to stay, I don't know if you guys stay within 225 amp panels, receptacle and lights. That's a good rule of thumb when you just throw your panels into the building. So we got these. 300 is close enough. We kept it. My lighting panel, the reason why my lighting panel is smaller than my receptacle panel amp-wise, guys, is because we're burning the lights at 480, 277. You can see that one. These are burning right here at 480. The receptacles, I wish we can burn them at 480, but we can't. We're burning the receptacle at 120. So here's your lighting panel, 175 amp. Then we go to the mechanical panel. I have two mechanical panels. One mechanical panel on the first floor, or one of them is going to be 400 amp, and the second one is going to be 600 amp. You can see I'm just going strictly by the next overcome protection device, right? So I have a 900, 394, 400, 600. I have 900, and then these are my two mechanical panels. My bus duct, I don't know if I have that one. Yeah. When I size for the bus duct size, guys, and for the actual panel size, and for the disconnect, this is my Bible. DeWalt, anybody have seen that? That's the new ugly. Yeah, I like it because I don't know, I know the circuit breaker size from an EC code book, but I don't know how they size the panels. Do they have a panel that's 350 amp panel, or do you jump to 400 amp panel? So this will give you the actual size of the panel for the most part. $18 we can buy it. So it's really cool. Bus duct, because where are you going to put the actual bus ducts? You can go to Square D, Color Hammer, make them, multiple manufacturers. Those guys have the actual bus duct sizes, industry standard, actual bus ducts. So the size is based on this number. So if anybody's wondering, I came up with a bus duct and the overcome protection device. This is also have to match the overcome protection device ahead of that. So I have 1,000 amp and 600 amp. And these happen to match what they use. But you really, in reality though, I want to warn you, you are sizing, you're sizing the overcome protection device, Then this is kind of the interesting one right here. Then you can go to, now we're sizing PDUs and UPSs. The last one is UPS and PDU, and I think I checked they make them. Now, I have, now remember, if you're familiar guys with UPS, typically we take one UPS and we feed a PDU from that, or two UPSs for redundancy, N+1 and 2 N+1, and multiple things. Typical, this is simple one, we decided to use two PDUs, feed them from one UPS, because we don't have money for the second one. So the size of the PDU and the UPS typically is the same. If you have two UPSs, we size them the same, and we load them 50%. That's how the UPSs we do them. If you have two UPSs, if you have two PDUs coming from the same UPS, you split them into 50-50. So if one of them goes off, the other one will be loaded 100%, typically less than 100% though, when we load it. So here's the load for the UPS. It happened to be 468 kVA. I went to the next standard, 500 kVA. I hope they make them. Thought I checked. PDUs PDUs is 500, the same thing, same size. And then I found the amps for them on the primary side. PDUs, guys, especially the PDUs, they have a transformer on them. I'm sure if you have dealt with them, they take the 480 inside a box that says PDU. You have a transformer on it, designed properly for the harmonics, and then they bust them together with multiple panels, typically 2 or 3 panels in the same box. And they feed all these racks with 208 voltage, 30 amp 208, or typically 30 amp 208, and they feed all these racks. And you plug in your service that cooks your, every time you slide your credit card, it collects information about all of us. So, so that the amp that you see at the bottom here is my amp on the primary side for the UPSs, and also on the primary side for the PDU. So I just took the value that I sized and divided by the voltage and came up with an amp with this amp. I came up with these 2 amps. So in order to size my conductors, the reason why I did that one, because I need to size my conductors on the primary side of the UPS and on the primary side of the PDU, right? I want to remind you guys, inside all these numbers is 1.25, already multiplied the continuous load. There is, when we were doing it, we multiplied by 1.25. I also sized the kVA of the transformer. I have 2 transformers. One transformer is going to be feeding the bus duct, 600, and the other one is going to be feeding the the receptacle. So I have 100 kVA transformer for the receptacle panel and 225 kVA transformer for the bus duct 28120 in order to shoot me 600, close to 600 volt amp. So you go strictly by the kVA, you know, to try to get you the next standard size, equipment, the next standard size equipment. After you do that, any comments, guys, about the kVA for the receptacle panel and the kVA for the 28120 bus duct? So, and all the sizes, the standard sizes, guys, of transformers are right here, or you can go to Cutler, Hammer, Square D, or any one of those guys. They can get you this information. So, and it's as easy as you need to be able to pick up the load in kVA, the next standard transformer. So based on after, you remember it's going to be based on after you add the 125 on it though. So, okay, so that's, and then gets the fun stuff. You go to 310.15b16. Got married, changed her name last code cycle. And also the one I use right here is 310.15b16. All of these are, guys, THHN conductor or THHN/THW conductors. If they're underground, you need the W. So I size them from 310.15b16. When I teach the exam prep, so the people will say, oh, which column I'm going to go deal with, Chad? In 310.15b16, there are 3 columns. The 60-degree column, the 75-degree column, and there's a 90-degree column. When you deal with the panels, the feeders, 3-phase, 99.9%, you are dealing with 75-degree lugs. So you're almost going to go directly to 75 in size. Unless you are derating, of course, which we don't group feeders, do you? Do you put a feeder for the receptacle panel and a feeder for the lining panel together? Now we have 6 or 8 current conductors, go derate, we don't do that. Feeders, that's one conduit at feeder. And if we need to parallel, we parallel them in separate feeders, in separate conduits. Okay, based on this, my friend, and right underneath there, the neutral, number 20, and these are directly from the code. Now, how do you deal with the neutral? With the phase, no problem. Go match the phase. When you size the overcome protection device for all these panels, go match the overcome protection device. Now, the code allows you, as we know, up to 800 amp, your conductors can be slightly less than your overcome protection device. I don't suggest that you do that, though. A good design would be match your current. If your circuit, if your panel is 225 amp panel, get a 225 amp panel cable or 225 amp cable. Match your panel. If you're trying to cut cost, a good cutting cost is try to take advantage of the 800 amp. Up to 800 amp, for example, you can have 2 sets for a 400 amp panel. For a 400 amp panel, I can pull either 600 kcm or I can pull a 400 amp KCM for a 400 amp panel. So both of them are right from a code point of view. From an engineering point of view, you put the 600. Think of voltage drop, guys. There's a lot of issues with voltage drop. So the higher in my mind, is always a voltage drop. Neutral. The sizing of the neutral. So let's just tell you how we size these then. Then here's my 4,000 amp. I use 11 sets. You can make them even, make 12 sets. And if you want to even them underground with ducts and what's not. 11 sets of 500 kcm, 3 conductors. No neutral. I haven't done the neutral yet. These are 3 sets. And each one of them will be, guys, in a separate conduit. They are underground PVC. The way we're going underground PVC. And we're feeding all these systems. Now the 300 amp panel, I'm pulling 350 kcm for the 3-phase. And you can see 3 watt for the 175. And I do hope I did these right. You can check one of them. Here's a 400 amp, for example. 400 amp panel, guys, you have 2 options. Either you can run a 500 kcm and you still meet the code, or you can run a 600 amp, and I strongly suggest you run 600 kcm. Same thing I'm paralleling for the 600, guys. I'm paralleling 2 sets of 3 conductors, 350 each. Same thing for the 1000 amp. I'm going to be paralleling if I'm to feed it with conductors. In the project, guys, I don't know if you saw that 1000 amp came actually directly and fed from the switchgear, so we don't need conductors. But if we are to size it with conductors, so bus ducts, you can have a feeder bus duct that brings all the power, and you feed it directly from a switchgear. I'm sure you guys have seen it. For the 600 amp, the panels, my panel, that's one of our panels. We have 2 sets. Same thing for these. For these guys, I size them strictly based on 602, 601, guys, 600 amp. And the reason why I did this one, because I had a question one time from a guy, well, where's the 1.25 for continuous load? Remember, all our loads, as we were adding them, we were adding the continuous, building it into the system. So it's already built the 1.25 when we size the feeder into the system, right? Remember, we were multiplying the continuous load by 1.25, so it's already built into it. You don't multiply it again by 1.25, so you could, if you want to. So that's all your sizes. Now let's go to the neutral, gentlemen. The same thing for the 100 amp, the panel, guys. My emergency panel, that's an interesting topic for an emergency panel. What are you going to do? How do you size an emergency panel? If you design the system, you take all your bug eyes, if you have bug eyes, and you add them up. If you have elevator on emergency panel, you add them up. If you have anything that need to be on the emergency panel, add them up and find the volt amp. For this one, we decided to go for 125 amp panel, smaller panel. It's a 277, mind it, 480 277 lighting panel strictly. And in this project, we decided to use some of the lights in the building with an auto transfer switch packing the emergency panel. So certain lights with a little relay will be used as an emergency light and a normal light. So it's flipped to the emergency upon the existence of the emergency. Long story short, we got 125 amp panel. We sized the conductor for number 3 for that one. Then we get into the neutral. Here's my neutral. The one I use all the time for neutral, guys, is 220.61. That's kind of my rule of thumb. The NEC code book says 2 things. When you size a neutral, you either add your neutral load, see what your neutral load, anything that's 3-phase, throw it out. It's not going to contribute to your system, like chillers and air handling units and what's not. And divide it by 480/277, and you size it. I personally would take that's one way of doing it. At the service, the NEC code book says the neutral cannot be less than the main bonding jumper, main bonding jumper, so you know how to size it at the service. But and a stability drive system, same thing. It can't be less than the main bonding jumper, so we know how to size the main bonding jumper. At the other panels, we really don't. We have to keep track of what our neutral load is. So a rule of thumb that I use personally is I use that fact, and it's typically engineered, pumped up a little bit. The code says if your neutral load is more than 200 amp, cut it by 70%. So I use this one as a rule of thumb. So here's what I apply. Again, this is an opinion, really, not nothing. So look at this here. This is at the main. I applied this one to the main, though, Though I could have used, when I sized this one, I could have used 500 kcm and went directly to 250.66 and sized my, based on 500 kcm, I can size my neutral with each set. You guys are familiar with when you size a neutral, the code says a neutral of the service cannot be smaller than the main bonding jumper. If you're paralleling, you can size your neutral based on the conductors in that particular conduit. So I want to go higher, a little bit higher than that. So I applied the 0.7. So the first 200 amp, leave him alone. Higher than 200, cut it by 7, add him up. So my neutral load based on a 400 amp, which is really extreme a little bit, is almost 3,000, shy of 3,000. Then I sized my conductor based on everybody knows how the 2860 coming? Then you size it, and I end up with 11 sets of 300 kcm. So my phases are 500 kcm, and my neutrals for the switchgear is 300 kcm. If you go to the main bonding jumper, you will get smaller than that. How small? When you parallel conductors, you cannot parallel less than 1 aught anyway. So wherever you go, you are limited. We're paralleling here. So the smallest neutral you can pull at the service is 1 aught. So that's at the service. I apply the same rule, guys, for all the other panels downstream. The same rule. The first 200, leave them alone. Higher than 200, cut them by 0.5. And size all my conductors for the neutral for each one of these systems. And then, any comments, guys, about sizing the neutral? And I would, if you guys want this sheet, let me know. I showed it for you. It's not a big deal, and critique it and give me your opinion on that. So we size the neutral, and we size the 3-phase and neutral. These are panels. Now the second thing, and ask yourself, guys, are we pulling? You need to size the grounding electrode conductor or the equipment grounding conductor, depending upon are you at the service or assembly drive system. So what we did. Okay, we have good time. So we have, I have this step 21 is called grounding electrode conductor or equipment grounding conductor, depending are you at the service or are you downstream, right? So to size the equipment grounding conductor, you go 250.122, grounding electrode conductor 250.66, soon to change to 250.102 something, the bonding. You're right there. So based on these, I'm not sizing the bonding yet. I'm sizing just the ground. Still there though. And based on these, guys, I came up with these numbers. Now you can, if you're using PVC, you have to use, these are my grounding electrode conductor, my equipment grounding conductor everywhere except at the service, my grounding electrode conductor. So at the service, it's my grounding electrode conductor. Everywhere else is my equipment grounding conductor. Now, if you have an EMT conduit, you'll get you there. A lot of us engineers like to pull extra. You don't depend on the EMT to ground you, especially at the panel, so you pull that conductor into it. So I have number 8, number 6, based on the and we size them based on the overcome protection device. So that's, I'm assuming here, and you don't have to do that, I'm assuming we're pulling a neutral even though we're using EMT conduits, which is approved wire methods for a certain length. The last thing you do when you design a building like this, guys, is you have to go and size the conduits, because ultimately the electricians and the contractors, and when we do AccuBid and McCormick and we take it off, we're going to be taking off conductors and conduits. So you need to go size your conduits. When I teach wiring, Mike, agree or disagree with me, I always say between, if you're indoor, your conduit of choice is EMT. If you're underground, your conduit of choice is PVC. Of choice. Now there's other options, right? So for the most part, if you have physical protection or hazardous location, rigid, threaded, right? Between EMT, guys, and PVC, it solved 80% of your wiring methods. Then you add a couple of MC cables. Only MC if we're doing a project. We don't use raw mix, I hope so, or AC cable. Add the MC to the mix of them. Your wiring method, MC, EMT, PVC, and MC cable, you're up to 95% on your wiring methods in most of the building. The rest of it is flex to tie to the equipment and maybe rigid if you have it in certain areas. So that's why in the service, we're going underground. We're going with a 4,000 amp switch gear. Schedule 80 is the best. So we could have used 40, but it is the best. So we end up with, now I want to remind you, gentlemen, we have 3 conductors 500 and 1 conductor 300 and 1 conductor, no, this is not inside it. I'm sorry, this is not, this is going to the steel. So basically this is size, it should be size based on 3 conductors 500 and 1 conductor 300. You end up with 3.5. Anybody want to check that? I hope I didn't. I used the calculator to size it. I just don't do the math. Now, a lot of us guys say a 3.5, put 4. So throw 4, it's nice, easy, even number. And you size your system for 4, for 4-inch PVC. Okay, same thing, gentlemen. The only difference here for the receptacle panel, I have 350 kcm for the phases, in neutral 300, and for the number 1 for the equipment ground conductor, which I might not need, right? You could use EMT conduit, and you end up with 1.25 inches EMT conduit to pull 4 conductors, 3-phase and neutral. I'm sorry, 5 conductors, 3-phase, neutral, and an equipment ground conductor. If you decided to pull it, which is a good idea, especially in the feeders. If there's mistake, it's mistake in the calculation, Mike. I clicked on the wrong number. This one?
Yeah, is that the feeder to the transformer?
This one here?
That column, or that's the K column.
The K?
Yeah.
That's for the receptacle panel. This is undersized, right? Can we size it together? Okay, here. THHN, right? Do you guys remember the sizing of, see, maybe I guarantee you, okay, so what was the size? 350, 300, and number 8, right? THHN all. Okay, you guys have used that calculator. So let's go 350. Here's my 350. Here's my K, wire size, 3 conductors, THHN. Okay, here you go. And what's the other one? Is 300, right? Here's my 300 K. Where's my K? Wire size. And how many of them? 1 and THHN. There you go. Add them up. And what's the other one? Number 8, right? Is it number 8? Yeah, number 8. Here's number 8. Wire size. 1 of them. Here's my THHN. Same thing. And there is my conduit. 2.5. Oh, I was drunk. Okay. Operator error. Good point. So 2.5. So see, that's why you guys are here, to correct me. That's why you have to keep an eye on the engineers when you're in the field. Yeah, all the time. You never know what they were drinking when they were putting this stuff. So, number 8. To tell you the truth, I was running fast through them, so I could have made a mistake. But the process, I hope you guys understand, the process is, you can go check it, but the process is right. The calculator is good though, but I must have pushed something or changed it afterwards. So that's basically, oops, let me go. That's basically, guys, what we do when you do a commercial calculation. I don't know if you go that intensive. That will size all your feeders, all your feeders, you know. I have 20 minutes. I want to show you a couple of, then we take it to SKM and do some analysis on that. Any comments before I leave this one, guys? Does it make sense to what you do for the most part? Yes, sir, Mike?
The electric shelf, is that obviously you can buy the thing you hold in hand, but is that a software or anything?
Yes, special people like Chad, you can buy it, but you're a trainer. No, if you're a trainer, they will give it to you for free. So contact them. Yeah, this is the calculator that we use in the field. This is an electronic version of it. Comes very handy though, both of them. But if you're in the field, this is your baby. And I just got updated to 2014, which is not a whole lot of changes. And busy-wise, you can stick a little chip in the back. I don't know if you guys, and it changes from code to code. I bought that one in 2008 cycle, and now it's 2014. And it seems, I tested it, seems it really worked good and fast. See how fast you click on that one? A couple of clicks back then. Hopefully it was right. So Any comments, guys? Any questions about this? Like I said, if you're interested in this sheet or any of the sheets, let me know. I pass it. If you see anything wrong, please bring it to my attention. I'm like all of you guys. I do my best judgment. I use some judgment like everybody else too. Okay, so what I wanted to show you guys is now when it comes to this is the feeders. Then you know, a lot of electricians don't have it. So what we do after you build the system, you take it in SCAM. How many of you guys have used SCAM? Just to see if nobody use SCAM. Yeah, you go build it into the SCAM, and then you can run some short circuit calculation, some actual sizes. So you might go, if you have that software afterwards, and change certain things, up them, change them, adjust them. You know what I mean, in terms of sizes and what's not. But what I use SCAM, my favorite was SCAM as when you guys size, let's take this, these are branch circuits. I like to check branch circuits when I do SCAM. When you do branch circuits, Mike, when you're sizing overcap protection device and using inverse type circuit breaker, your multiplier will be, to size it, is 2.5, right? 2.5 times the full load current for that motor, and that's how you size, yeah, how you size your, I didn't mean to put you in the spot. Let's go look at this. So this is a really handy calculation that I use to check it all the time. Just to show you, let me show you. Here's this is a 75 horsepower motor, directly 75 horsepower. One of the ones that you looked at, and I need to size the overcam protection device for it. Now the code guy says you take that full load amp and you multiply it by 2.5, and that's how you size your inverse type circuit breakers. Or if you use fuses, no problem. What type? Dual element time delay fuse, 1.75, non-time delay fuse, 3. And then you end up with oversizing the fuse with circuit breaker, because you don't want it to trip. So here's what I always suggest if you're doing motors like this. Always ask for, so here's my starting, now they have VFDs on them, VFDs, right? Now when you have a VFD on them, that starting current, you can see right here, that can go way down, because you start at not zero, but you start at really low, very low VFD. So that starting current can go way down when you have a VFD. So there is no need for you, unless you have a VF bypass for the VFD, then you have to start it without a VFD for whatever, mechanical or whatever. There's no need for you to go too high. And if you guys remember the instantaneous right here, this is the instantaneous circuit breaker. What I suggest, long story short, if you're dealing with motors in a 3-phase, always ask for an instantaneous adjustable circuit breaker. And they're perfect. Anything, sorry? Yeah, instantaneous adjustable circuit breakers. So they're molded case circuit breakers. They're cheap, still cheap. The only thing you can adjust is the instantaneous. And the reason why we do the instantaneous, then we can undersize or not oversize the circuit breaker, which means we can lower the arc flash, the available energy from the arc flash, because now your instantaneous is down, you're not allowing it to go too high, and have a lower PPE and all this good stuff. So if you're doing design, always on especially if you're an engineer, always ask on chillers and rooftop units and all this stuff, at least an adjustable, if they're using circuit breakers. If you're using fuses, always ask for a dual element time delay fuse, because 175 is easy versus 300, you know, in terms of arc flash, energy, and what's not. So here's what this is. I have 100 amp. I'm using a HKD 100 amp 65 KA, expensive one, 480 circuit breaker. That's a collar hammer. In the trip on that baby, it's 100 amp. And I'm sitting at 100 amp. Can you guys see the instantaneous? If I put it this way, now my motor will never start. This is adjusting the instantaneous. I can set my instantaneous 5 or 10, and then when you set withdraw, you 10, you move the instantaneous. It allows your circuit breaker it allows your motor to start. That's if there's no VFD, you know. So that's what I say. The adjustable circuit breakers can allow you to adjust them really good in terms of allowing the motor to start and at the same time not oversize the circuit breaker, not oversize circuit breaker. Do you guys want to go size now? Let's. I came up with 100 amp for this 75 circuit breaker, 75. What was it? 75 motor. What would you now? Circuit breaker, mind it. Let's go to 75. Let's go size it based on the code, shall we? How much do you put 100 amp? Let's go size it based on the code. Show you the calculator as well as long as we're on it. So this is how you use this one to size overcome texture device. So my voltage system is 480. Here's my volts, and I have, what is it, 75 horsepower. I have a 75 horsepower, and that's where you put your horsepower. And then I need the full load amp. Here you go. Here's your full load amp, 96. Can you beat that one? Can you get this one from the code faster than that? By the way, I don't work for those guys. Now your full load amp. Anybody want to check if that's the right full load amp from the NDC code book? Okay, now let's go size the inverse type circuit breaker. You see that little bind here? Here's your inverse size circuit breaker based on the code. This is 240.62. You go down to the next standard up, that will be what? 250 based on the code. So your circuit breaker can be 250 as high as 250. You don't have to go. So if I go based on the code, my circuit breaker here at 250, if I actually go based on the code down, which you're allowed to go down, 200 or what, 225, I can go down to 225, right? 242, 225. Now, did you see that? Now, what I did here, I went to 100 amp. I was able to do a full protection for that motor based on 100 amp. I don't know if you guys can see that circuit breaker right here. 100 amp circuit breaker by having an adjustable circuit breaker and slightly maybe more expensive circuit breaker with 100 amp. So what was it, 95 the full load current? I went just above the, even better than the overload. And also you can show the overload protection. I don't know if you can see this. You can show the overload protection right in here too. You can, so what it's good when you have, especially for engineers, when you're doing the branch circuit, guys, try to instantaneous strip circuit breakers, specify it with major equipment, and then you can go check it and size it based on SKM, and you can tell that most likely, granted everything is okay, which typically they are. I mean, SKM is a well-respected software. You can get from 250 down to 100 amp, and you don't have to go that low, but just I use this as an example. So that's an example how we can go much lower than one in the secret book, and still by doing it this way, you reduce arc flash on that controller, if you have a controller to work on that, PPE, lower category, safer, right? And that became after, you know, the whole, when you move it this way, guys, every time you move it to this, you're allowing the arc flash short circuit, the short circuit arc flash to sit longer on your equipment for a longer time, and that's where you get, you know, too much energy and burning equipment and what's not. One thing we do also, I was doing the medium voltage today, and we talked about a little bit is, this is called the damage curve for the conductor. It's not a big deal for, just show it here because it's here. When we size, this will show you the conductor size that I'm using is number 1. I can't remember what would be with the, based on the code. If you guys can go size that would be correct, number 1, yeah. I wasn't drinking coffee at that time. So you can oversize it here. You can go up. If you go to 1 aught, you can see it moves up. This is called the damage curve, which will show you that your conductors will be able to survive a ground fault or a short circuit condition. Not a big deal in low voltage, 600 volt or less. A big deal when you have a high voltage system, 13.8 if you do 13.8. You always have to look at your damage curve for your medium voltage cable. So that could be a great application for that. So so that's what I wanted to show you guys. There's a couple of other curves. I use them if you have the software. If you're an electrician, you guys don't have them. But if you're an engineer, take advantage of these. They come very, very handy when you deal with them. Let me show you another one we have for transformer chiller. I have a receptacle panel. Here you go. For receptacle panel. And again, I was running a couple of scenarios here. If you have a switchgear, This is just to show you how a switchgear adjustable, fully adjustable circuit breaker. This is what a fully adjustable circuit breaker is at 4,000 amp, the one that we just sized. You can see you can adjust the long time pickup, long time delay, short time pickup, short time delay, and I deleted the instantaneous here on these. So anyway, so that's, you always keep in mind that right now, especially with the 70E and with reducing the arc flash, you'll always be better. I want to emphasize that one. I don't know if you guys can see that little inrush for the transformer. So for example, if I move this one in here, that's feeding the receptacle panel. Now every time you start your motor, your transformer, or when your transformer is energized, it will trip because you have to clear. So what we do is we shift it up, but you don't want to shift it, the further to the right you shift it, the less safe your equipment would be. So we try to kind of adjust, and there is IEEE standards, how far you can go and what's not. But that's if you have an SKM and you're an engineer, that's another source that's really good to apply for your brand circuit. And I check them most of the time, guys. I do them for transformers and motors, and I do have one. If we have, I'm not sure if we have it. We have a few seconds here left. If I can have it here, not sure if I have it on the generator. Okay, I don't have it on this project. But you can do them in any of these. This is for the chiller, and then you have a ground fault protection by code. If you have 1,000 amp or higher, 48277, you're supposed to have a ground fault protection in your system, so you can do your ground fault protection and coordinate. This is, you can see all these coordinated. This is the main for the building. This is the main for the mechanical panel, and this is the main for the chiller. The main for the chiller. I'm sorry, this is generator. I'm sorry. We have a generator. We do have the generator. Here's my generator main, and here's my main for the building, and here's main the chiller. The chiller was fit directly from the main switchgear, so you can see they're coordinated. So my chiller is fully coordinated with the generator feed, if it's fit from the generator, or from the service, which is normally fit from. And it has a VFD, so really this doesn't even have to, you can go, but we don't, you can tweak it if the VFD is there, tweak it down here and make it safer. That's on the fully adjustable circuit breakers. So if you're dealing with, I always say, and I do have interruption issues, I have to raise the interruption here, but if you have 1,000 amp or higher system, if you're an engineer, adjustable circuit breakers are awesome. If you're doing circuit breakers on machines, I would say 30 horsepower or higher, having at least instantaneous adjustable circuit breakers will allow you to have a smaller size. Any comments, questions, guys? So I hope it wasn't too much. So this presentation, guys, will be on YouTube tonight, my channel, because I'm recording it. I don't know when you guys want to put it on yours, but and the other thing, if you guys need any of these curves or any of the stuff, email me. Let me put my email so you can contact me if I can be of any help. Let me see. Put it right here. Okay, here's my YouTube channel here. Doesn't have to be capital. .edu. So oops. .edu. ccurdy@dunwoody.edu. If there's anything I can help with, guys, let me know. And I believe that's all what I have for you guys. Any questions? Any comments? And I hope I didn't I didn't sound too much engineering. But thank you for correcting me. That's why we have you guys. Keep an eye on us so that the conduits are straight. Thank you, guys. Thank you. Yes, give me a second. Here you go. Thank you. It comes really handy. 100%. And I'm on record here, so give me 1 second.